Hello everyone and welcome to the third of four webinar series here at Magic. On the 16th of October we had our second webinar about the systems of systems engineering as a set of developing processes, tools and methods for designing and redesigning complex systems. And today's webinar will cover the engineering analysis on SysML models. To be more precise, this session will demonstrate state machines execution, activities execution, action language helper, SysML parametric execution, integration with external math engine, in particular MATLAB, combined model execution, building executable user interface, and generating execution trace. The session will be hosted by Dr. Aurelijus Markevičius, OMG Certified UML Systems Modeling and BPMN Professional. He has been with Magic since 2008 and now he is a Senior Solution Architect for Model-Based Systems Engineering and Defense Architectures. Aurelijus is working with companies such as General Electric, Kongsberg Defense and Aerospace, BMW and Deutsche Bahn. He also passionately participates in various activities of modeling standards creation. He is a chairman and one of the leading architects for the current OMG UPDM standard development group. If you have any questions during this webinar, you can send them to us by using a chat module. After the presentation, Aurelijus will review the questions and answer some of them live here. Other questions will be answered later and will be presented together with a video link of a recorded webinar. The presentation will take approximately 45 minutes and the answers to your questions about 15 minutes. Aurelijus, are you ready to start?
Yes, I am ready. Thank you for the introduction. And it's nice to see so many people joined. Hello everyone. We will start our webinar on engineering analysis on SysML models. So first, this is agenda for the webinar. I will introduce you to model-based engineering analysis standards and activities. Then we'll have introduction to Cameo Systems Modeler, capabilities for engineering analysis. Then, of course, live demonstration using Cameo Systems Modeler on how to execute systems models. And then questions and answers session as it has been mentioned before. So on this slide I want to emphasize the model-based system engineering ecosystem that is provided by Magic. Some of you already watched webinars before, webinar 1 and webinar 2, where we covered some of the capabilities displayed here. Today we will talk mostly about simulation and co-simulation. These are capabilities provided by Cameo Systems Modeler. And of course it is related to some external tools like MATLAB, Maple, Model Center, Wolfram Mathematica, and other that are used for co-simulation purposes. Just quickly before we start going into concepts, here is shown the Cameo Simulation Toolkit product, which is a plugin for Magic Draw. So this is just for explanation that these two products together actually forms the Cameo Systems Modeler, which we are going to use for this demonstration. And the Cameo Systems Modeler is a model debugging and animation environment. It allows to plug multiple engines, languages and evaluators inside to perform some mathematical calculations. It also provides user interface prototyping support and of course model-driven configuration and test cases. Now let's talk about standards. So first of all, activity simulation inside the tool is based on Object Management Group Executable Foundation for UML standard, fUML. State machines, they are based on State Chart XML standard from W3C. Then we support actions and expression standard JSR223 for scripting languages, and of course SysML parametrics. Besides standard-based model execution, we also provide composite structures execution, instance specifications, and execution of sequence diagrams. So why I'm talking about standards, it's because there are a lot of different execution environments and execution methods in the market. And this slide shows the poster from NASA where they emphasize and where they say that it is important that UML simulation toolkits such as Cameo Systems Modeler, they are tools to interpret model instead of relying on generated code. So actually Cameo Systems Modeler exactly interprets model directly. It does not generate code which is further used for simulating systems. And this is important, of course, to rely on standards, because organizations that do not comply to standards, do not comply with standardized approach, suffer from loss of capability to inter-exchange their analysis models, to communicate with other development teams. Of course, it creates overhead in tool customization, specific training needs, and of course the problem is that models become impossible to integrate and reuse. So these are the main standards that I mentioned here, and actually this study is posted on our blog, where some of the tools they are compared and capabilities of supporting standard execution methods. So this is the link to visit our blog and to read more. So let's talk more about the capabilities that I mentioned. So first is simulation. And why simulation is because the purpose of simulation is to gain system understanding, to explore, to understand its behavior, and of course it's the basis for performing engineering analysis on SysML models. So when we have executable system that can be simulated, executable model, a system that can be simulated, then we of course can perform engineering analysis. So this is the entry. And let's talk now about executing activities. So executing activities is the first step that's based on standard, on OMG standard, Foundation for Executable UML. And so the basic is that activity diagrams, activities itself, they specify behavior as execution of set of actions, right? So it includes multiple actions. An action itself is the fundamental unit of computational behavior. There are multiple different actions available, and actually more than 50 actions are available inside UML, and they are for different purposes, of course, such as send signal, receive signal, opaque action to call scripts, call other behavior, and etc. So there are a lot of actions. The idea of an action is to take a set of inputs and convert them into a set of outputs. So it takes inputs and transform them into outputs. And action in one activity may call another activity. So some of the actions, so-called call behavior actions, they can call other activities that have multiple other actions and different flow. And all the actions, they are connected using data and control flows, and it's all about data and control tokens flowing between the actions. So data flows between the actions, the inputs come into one action, and then they are transformed, and the outputs flow further. The other important thing is execution of state machines. Execution of state machines provides a little bit different semantic and different engine. It's based on state chart XML execution engine, and the system, when we talk about states, the system is modeled as having discrete transitions between the states. So we have states, we have transitions, we have many different kinds of states, and we can associate states and transitions with different behaviors. So for example, behaviors can be associated with transitions, so it means if some event occurs, trigger is fired, and we transit from one state to the other. And then behaviors can be associated also with states. For example, entry, do, exit behaviors, they can be applied. So state machine is used as the main behavior for the block, for the system, to control all other behaviors. The other behaviors that we are talking about, that they can be called from state machine, they are activities, as we talked before, opaque behaviors based on some script, interactions, and other. So basically, state machine defines the life cycle and provides the control for other behaviors. Then executing SysML parametrics. SysML parametric is a specific kind of diagram that provides capability to connect mathematical equations to your system parameters, take values from them, store values for other parameters, and this means it forms a network of mathematical equations that can be performed. So it's in Cameo Systems Modeler, it's dynamic expressions evaluation. It means that if at least one of parameters change and it's related to a network of mathematical equations, it means they're automatically invoked and recalculated, and the results are stored. So it's part of other executions that combined together provides a powerful tool to analyze your systems. Now let's talk a little bit about co-simulation. So it's another important aspect of Cameo Systems Modeler and engineering analysis. So when we talk about co-simulation, we are talking about different tools, different functions from different tools linked together. And the SysML model here acts as coordinator for this. So we can add some values into execution. We can put these values for a MATLAB function as inputs, then perform this function, get results in our activity diagram and SysML model, then pass these results to other tool like Maple, or just perform some JavaScript with these operations, and then output to other tool, and output as the result of activity. So basically combining different scripting languages that are shown here on the slide and mathematical engines such as Maple, Mathematica, MATLAB, and also object constraint language, we can create a co-simulation scenario inside Cameo Systems Modeler. Let's talk a little bit about math engines and math engine support that is provided. So first of all, there is built-in math engine that we're going to use mostly. But built-in math engine doesn't provide some sophisticated functions. So for example, if you have some functions, we have some models like Simulink models. For this, it's MATLAB that should be used. And other, like both for Mathematica and Maple, they're also supported. It means there is support of remote solvers, the causal solving, parser for MATLAB M files. Also, we allow direct function calls from activity diagrams, and we provide import-export of variables into mathematical environments. So this is example of calling external functions, where we call XLS write function. It means that we write some values into Excel from activity diagrams. So we define language, which is MATLAB, and define body. So body is the MATLAB function that is called directly from the model. The other example is invoking Simulink model. So if we have very simple Simulink model, it can be called using MATLAB function sim with the parameters required. Then the model is executed, and the results they are acquired into the model and produced as the output of the action, and then they can further used in other models, in other execution environments. And so this all the simulation and co-simulation, it's background for performing engineering analysis, and our tool can also be used as automatic decision tool. It means evaluating different designs against selected set of requirements and criteria. to choose best available alternatives for design, to verify requirements, to check their compliance. And so this is very important, and it's also related to all the simulation and cost simulation activities. The engineering analysis that can be performed is evaluating design alternatives, selecting best set of parameters of all available, verifying system constraints, performing requirement compliance analysis. We see some of this during live presentation, and perform what-if analysis, and execute SysML and UML testing profile test cases. So constraints verification is performed at runtime. So it means that if you have some constraints defined and you run your system, you execute your system, you can check whether your requirements are verified or not in a particular moment in time. So it means that then you can get a snapshot of the system. At that time you can see requirements, you can see parameters, you can see requirements, so you can see which parameters that failed and parameters that produced results based on the requirements, based on expectations. So you can perform more analysis and find out what the reasons are, try different alternatives, different variants of system, and check this again, export results, and then we're going to see this during demonstration. And so this is related to trait studies. So trait studies is exactly performing multiple tests based on some criteria, finding best results, best fitting results configuration. For example, in the table in the bottom of the slide, there is trait study performed on different engines, and the most powerful engine is picked as the winner in each of trait studies. So this is just one of examples. We'll have another example during live demonstration. And the last aspect that I want to talk here on this presentation, on the slides, is user interface prototyping. So we provide diagram to prototype user interface. So the user interface then can be executed, and signals can be sent directly into the system to start execution, stop execution, provide some inputs, and get some outputs displayed to the user. So this all is related. We're going to see that, and this is example of diagram on the left side and executed user interface on the right side. So we are going also to build some user interfaces during live demonstration. So now we are going to a tool, switch to Cameo Systems Modeler, and I will start from a very basic explanation of how to execute state machines, how to execute activities, how to execute parametrics, and how they all fit together and perform a single execution for the system. Then we are going to build user interface. We build different configurations, and finally we generate trace. We generate sequence diagram as a trace for execution. So this is the first part of live demonstration, and the next part then quickly going to more sophisticated model and performing some trait studies on coffee machine and rotary pumps. Okay, so I have a clean project here, so I start creating elements, and my simple system that I'm going to show will be timer. So it's a really simple system, and I'm going to create a new block directly in my model. My block will be timer. Then I'm going to create a value property inside timer. So value property will be time. I also add type for it. So it will be integer. So here I'm going to store the time value from the execution. Then I create state machine, simple state machine for the timer. I go and create new diagram, SysML state machine diagram. I give a name for a first state. It will be on state. It will be off state, and also I have one more state which will be off state, on state. Excuse me. Okay, and then I create transition between the two. Now as I define transition, I need signal. So I need someone to trigger the transition. So for this I'm going to create signal, and I get back again to the model. I create a new package. I say it's signals. And here inside signals package I create new element which will be called start. So it's a signal element, start. Now if I want to say that it's used as the event on transition, I just simply drag and drop it on the transition. So I associate signal with transition. Then I create another transition going back from on to off, and here I create new signal again which will be stop. Take stop signal and associate it with the transition. So this is a very small system. Now let's try to execute the system. So to execute the system, I go again on timer block, right click, go into simulation and execute it. As I use MATLAB for mathematical equations, the math engine is started. Okay, and then I can start my session. So as you can see, I'm currently in the off state. As I don't have any user interface or any activity sending signals here, I have to do it manually. I need to say that, okay, send start signal. When I say send start signal, I go to on state. Then again, if I click stop signal, I go to off state. So it is very simple. Let's make it more complicated. So now as it is timer, when it's on it should tick. For this we are going to create activity diagram inside the timer, and we call this diagram tick. Okay, so let's create a very simple diagram. I create initial node. Then I create opaque action. I use it for a simple script where I say that my time equals time plus 1. This can be modeled using UML, complete UML only, without any scripting. But instead of having one action, you would have three. One for reading value, for reading self object, then reading value, and then adding value to the object. So using scripts sometimes is easier, right? So we say that from the start we go to increase time, and then we go into activity final. So this is very simple activity. To associate this activity with our state machine, we need to get back to state machine diagram. Then we take our activity and drop it on state. In that case, we would say that it's entry, do, or exit behavior, right? Also, there is another option that I'm going to show you. If we are going to create transition to self on the on state, it means that each time it's triggered, then it gets back to the on state. We are going to define time event for this. We are going to say that it ticks every second. So we are going to create time event. We are going to say that it is relative time event. So it means that it happens after. And we say that after 1 second. So we specify time event. Okay, so it is defined now. Now we take our activity tick and say that after 1 second, tick happens. So we associate our activity, dragging and dropping it onto transition, to the transition as the effect for our event. So now it's all set. I can show two diagrams at a time. I can show activity diagram and state machine diagram, and we can run timer again. Just switch to another diagram. Okay, and then we run timer. Okay, so when we send start signal, we go to on state. Then we can, as you can see, it goes into activity, it increases time, and here is also variables pane. Let me show it to you so you can see it, where we can analyze variables and their values. Here is animation turned on, so it's actually slower than the exact time, and if you want to make it exactly 1 second each tick, we should turn off the animation. So currently, as you can see, time keeps increasing, right? And we can see how is it running. So we combine states and activities execution. The next thing that is related to all this is parametric diagram and parametrics. So we are going to create a new parametric diagram for our timer, and it is going to convert our seconds into minutes. Okay, so we go on to timer, we create new diagram, SysML parametric diagram. We can choose here from value properties that we have. Let's say time. Then we create constraint here directly in the parametric diagram, and we say convert seconds to minutes. Then we can add constraint expression, and we can say that m equals s divided by 60. It's very simple mathematical expression. Okay, then we associate time with our constraint. So we say it's s parameter, which goes for seconds. Then we are going to create a new value property here, and we say that it's a real number, and we are going to add name for it. So it will be time in minutes. Okay, and we associate it with constraint as well, and we say that it is our result. Right, so it is very simple parametric equation that, so now when we run this all again, right, we go to timer, we say that we want to run this, and let me open our variables pane again. Okay, so in our variables tree, let me do it floating. And let's start the simulation just to see how the conversion works. Let's make it a little bit faster. And then, as you can see, time in minutes, it gets value, and constraint is evaluated, and the result is provided. This happens because time is changing, and when the time change, then all the equations, constraint equations, parametric equations related to time property, they recalculate. And so then time in minutes gets increased. Okay, so let's stop the execution now. The other thing is I show you how to create user interface. So for this, I'm going to create a new package. I say that this is my graphical user interface, and here I'm going to create a new diagram. So the diagram is called user interface modeling diagram. Okay, so the diagram is created. Let's call it graphical user interface. And here I simply create frames. So this is the most important element here, right? So then I can take my timer and associate it with frame, just simply drag and dropping. So it means that this frame now becomes representation of a timer. Then I can simply go into timer properties like time, right? I can drag and drop it directly onto frame. I can do the same with time in minutes. Right, then I go to signals and I take signal and drag and drop it onto the diagram. So I say that this is my start and this is my stop. So these buttons now will send signal to our state machine, to our system during the execution, during the run. So it is very simple graphical user interface. So to make it work, now we need to create another diagram for execution configuration, and it's also another important concept that I want to introduce you. So it's simulation configuration diagram, where we define all the properties and parameters for configurations. And we can set up multiple configurations for different scenarios and different, for example, user interfaces. So here we can say that our timer, this is our timer 1 configuration. We take our timer again, we drag and drop it on timer 1, we say that it's execution target. Then we go into more properties. Here we have user interface. So we need to associate our user interface, which is created in our model. I just make it timer 1 because I'm going to create another user interface afterwards. I take it and I drop it inside the user interface. So I associate user interface with this execution configuration. And I also can say that my execution will be silent. It means that no animation will be shown, right? So it is going to perform much faster. Okay, so this all configuration is created, and as soon as we create the configuration, as you can see, it appears here on top. So if you have a list of configurations, you can choose one, and then you can just simply click run. So as you can see, our user interface is shown, and here we can start. So it means that we send start signal to our state machine. You can see time is increasing. We can stop and we can start again. So this is a simple example of creating user interfaces. Now if we go to graphical user interface diagram again, and let's create another graphical user interface just to see how it works. Alright, so let's do it smaller. We take our timer, and here we show just time in seconds. Let's say we don't care about time in minutes. Just to make it more interesting, we can go to symbol properties and say that we want to make it yellow. And then we just simply drop our buttons, right? Our signals. Start and stop. Now we go to execution configuration diagram and we create another execution configuration element. We say it's our timer 2. We do exactly the same. We take timer, we say that it is execution target, we go into specification, we set our user interface, a newly created user interface, and it's already silent, right? Okay, so we created new execution configuration. Now in the list we can see two of them, timer 1 and timer 2. So now we can go and run timer 2 configuration. So you can see the graphical user interface is different, and it also performs all the same tasks as the first configuration. Okay, so let's close this. Also, another thing here on this model that I want to show you is backgrounds of requirements, requirement compliance analysis. So for this, let's create a new package and we call it requirements. Then inside this package, we are going to create new requirement diagram. Here we create requirement. We say that this requirement, the requirement is no more than 10 seconds. So as soon as 10 seconds pass, constraint should fail. So it's very simple just to show how this works, right? And I add text, no more than 10 seconds. Okay, so this is our very first requirement. Then I take my timer block that I have created from my model. Let me take my timer block, I drop it here. Then I say that my time property actually satisfies my requirement, right? So I create traceability between the two, between architecture and between requirements. Then I need to formalize this requirement to make it work. So for this I need to create another constraint. So I go back to my model and I create a new constraint block here, another constraint block, and I just simply call it no more than 10 seconds. Okay, and I can show it here on the diagram. I can say that it refines my textual requirement, right? So again, create traceability and refinement. Then I can add constraint here. I say that the constraint is very, very simple. It's time less or equal, let's say 10, right? Our requirement is 10, less equal 10. So it is very simple, a verifiable constraint. It doesn't return any value as we saw previously. So the final step here is to go to the timer and create new parametric diagram. Again, new one. And here we need our time. We don't need any other properties. We take just time. Then we take our constraint block that we created, no more than 10 seconds. We drop it here. We say that time is associated with parameter t. So this is all the association that we had to do, and now we can simply go and execute our timer again. When we execute this in variables pane, we can see that while it's 0, requirement no more than 10 seconds is satisfied. Then when we run this, and we send start signal to the system, right, to make it start, you see it increasing, and the time is satisfied. Until it reached 10 seconds. When it passed this, we can see that requirement number 1, no more than 10 seconds, is not satisfied at runtime. Right? So we see that there is some kind of problem with our system configuration. And there is no stoppage at 10 seconds. Okay, so let's stop this configuration and let's move to another example. This is very simple example, just to have understanding and basic idea of how engineering analysis can be performed. Now let's go to more sophisticated example. Let me quickly explain what do we have here. So first of all, here we have requirements, and well, actually just before going to requirements, the case here is rotary pump for coffee machine, and we want to pick the rotary pump that is best from available variants. So if we have a table of available pumps, Here we can see power, here we can see flow rate, it means water that flows, right? We can see mass. And we have requirement also defined that watt hour, that it's the power used by rotary pump should not exceed 7. For this, we have, of course, here all the design for the rotary pump and for the coffee machine. If we go for the coffee machine, we see inside, and we see boiler and rotary pump, and we can see how rotary pump pumps water into the boiler. So these are ports displayed, and the value inside ports shown that the water is what flows here, right? From rotary pump to boiler, and when boiler is filled in, it sends signal to controller that is already full, and turn off the pump. So this is our design, and then finally we have test cases. So we have test cases, we have 5 test cases, and all of them are different. So there are 5 variants of coffee machines with 5 different rotary pumps. And we need to choose best pump according to our requirement. It means energy consumption, right? Then if you want to run a test, right? If you want to run test 1, just before that, let me open the analysis results here where our tests will be stored. So I start to run test 1. I execute test 1. I just make it fast, to not wait. As you can see in our variables pane again, let me do it floating. Energy to fill is increasing. We have requirement. We are verifying the requirement. We have coffee machine power here. As we can see, the first pump already exceeded limit, and it stopped, right? So it is stopped. Now I can export results into my results package. So I export results. As soon as I export them, I can see them in a table, right? Results table. So case 1, coffee machine 1, time to fill 16 seconds, and energy to fill 8.8 watt hours. And here is also mark which says whether the test was satisfied based on our requirement or it wasn't satisfied. We can also change a lot of different parameters, other parameters, like we can say that boiler capacity is bigger, right? And then see what happens then. So capacity here is 3 liters, by the way. So let's run test 2. Let's find one which is, let's first stop the execution of existing test, and let's now run test 2. Let's run test 2. Let's see what happens. The boiler is filling. We can see this happening here inside the boiler. As you can see, capacity is 3 liters and actual capacity is 2.47, and it's not filled yet, and requirement is not satisfied, right? So finish the execution. We export this to results. This, of course, possible to set up this automatically. It's just I make it manually to show you the idea of what's going on, because if you see just table and just run button and how everything completes, it wouldn't help to understand how all this works, right? So we close this execution and we start again another one. Start again another one. We see how it's going. Okay, so it finished, and as you can see, requirement is satisfied. We export results into our table. We see that energy to fill is 5 watt hours, and requirement is satisfied. Then we see what kind of coffee machine it is. It is coffee machine number 3, and we can get back to the previous table and see that variant 3 of the coffee machines is the best one, which has power of 300 watts and flow rate of ½ liter per second, and mass of it's half kilograms. So this is the best variant. We can save it as the default configuration, and we can use this as the best alternative. So that's it about demonstration. Thank you for watching. Now we move to closing, to questions and sessions, to questions and answer session. If you have any questions, please write questions directly directed to the area for questions, and we answer them now, or some of them, if there will be a lot of questions, we can answer after the webinar.
So we have one question. Which calculation engine is used to run the simulation? MATLAB or other?
Okay, so actually here on my machine that I demonstrated, it is MATLAB execution engine that is running. I have MATLAB here open, and here it's also possible to see, if you look into console, you can see the results from MATLAB in the log of all the functions that we used. But these simple calculations that actually we used today, they can all be covered and can all be they can all be solved using built-in math solver. They're not sophisticated that they would require MATLAB. This all can be done just having Cameo Systems Modeler. Thank you.
We got another question. How do you reference a block state in a calculation?
Well, actually, in this example, state itself is, if I understood your question correctly, the state is not referenced, but it is possible to check what the state is, to add constraint, for example, that would check what the state of the block is. There is an action language helper for this called inState, and so then you can use it, and you can check in what state the current block is, and use it as the condition, as the constraint, or whatever.
Are you sure the simulation toolkit is included in Cameo Systems Modeler? The website says different.
Starting from version 18, it is included into Cameo Systems Modeler Enterprise Edition. If you go for Architect Edition, then it has a separate plugin. But if you go for Enterprise, it's included into Cameo Systems Modeler.
Is it possible to make your sample trade study model available?
Yes, I think this is possible, and together with the recording and questions and answers, we can also share models used in this demonstration.
Which stereotype is used to represent variant, UML or SysML?
Actually, here in this example, there are no stereotypes used for variant representation. It is simply instances that are made out of a design model. So if I have rotary pump as the design here, I can instantiate it and create instance specification. And each of the instance specification, they have their different values, but they are all of the same rotary pump type. So the values are different, and I use these instances into execution engine. So the variation here is done at the instance level, but not in the design level.
How does the Cameo modeler differ or complement Parametric plugin?
This is a very good question. We had this analysis together with Parametric guys, and we tried to identify what the differences are. So basically, on most of the cases, Cameo simulation toolkit or together with Cameo systems modeler, it's more powerful. It provides not only parametric solving, but also behavioral executions. In terms of parametric, it's more simple. It's easier to build your execution that in case of using Intercac's Parametric plugin. But on the other hand, Intercac's Parametric plugin provides some more sophisticated integrations with some of mathematical engines. So there are some advantages and disadvantages of both of them, and this needs to be analyzed dependent on your needs.
How does time integer is associated to activity time equals time plus 1?
It is by the context and by the text match. So if there is only one time concept inside the context of executable in the system of the state machine, for example, or activity, in this case in the timer, so this is recognized and evaluated. So this is actually by text.
Can the product do code generation from the models?
Yes, it can. Dependent. Well, it's again, it can do code generation from structure. Talking about behavior, it requires some third-party tools to be integrated.
Follow up on the parametric question. Is there a white paper or something that can compare and contrast parametric versus Cameo Systems Modeler to assist in evaluating what is needed?
Well, I'm not sure if there's a white paper, but if you could write us an email, we definitely find something that we can share. Yeah, I think so.
Which third-party products are needed for code generation of behaviors?
Well, it depends on what kind of code you want to generate. If you want to generate embedded code, so it's a Intel Confluent Studio that we're working with. If you want to generate software code, well, I'm not the best expert on this. I need to check this, but I think it's Willard. This is the name. I think there are some more third-party plugins. There is a plugin from NASA that they have built for their needs, and it's also open, I think. And also there is Andromeda framework. So we can actually, if you could write email, we could provide you with more exact answers to this question.
So thank you everyone for participating in today's webinar. Thank you Aurelius for an interesting and informative presentation. If there is anything we didn't cover today, or you got some more questions, please do not hesitate to contact us anytime. And the next and the final webinar will be about defense systems engineering with NAV and SysML, and will be held on the 10th of December. So again, we hope you will add this date to your calendars and join us in December as well. We appreciate your feedback, so our webinars would get even better. To learn more about model-based systems engineering solutions and about our webinars, you can visit our website. The address of this website you can see in the screen right now. So thank you again for your time today, and we will be waiting for you to join us in December.